We all know the very famous Pythagoras theorem, a square plus b square equals to c square. And these three integers a, b, c from this equation are called Pythagorean triples. Our task is to find Pythagorean triples. So go ahead, try to think of three integers a, b, c that might work in this theorem. The first thing that might pop into your head is 3 square plus 4 square equals to 5 square. And if you do the math, 3 square plus 4 square equals to 5 square is a true statement, which means we have found our first Pythagorean triple, 3, 4, 5. What if I want to find more Pythagorean triples? Since we have already found one Pythagorean triple, it will be easy for us to find more. We just have to multiply these three integers by any number. Let's say we multiply this triple by 2. We get 6, 8, 10. Now that's another Pythagorean triple. We can multiply by 2 again to get 12, 16, 20, and that's another triple. And we can keep going, and all of these triples will work in the Pythagoras theorem. And just to be clear, they can be multiplied by any number, not only 2. And we have essentially gotten unlimited Pythagorean triples. But that's a little too easy for us today, so I'm going to introduce a new factor. Instead, we will be more interested in primitive Pythagorean triples. These are Pythagorean triples that don't have a common factor. That means the cheap trick of multiplying the triple by another number won't work. For example, 3, 4, 5 is a primitive triple. 5, 12, 13 is another primitive triple. 6, 8, 10, however, is not a primitive triple since 6, 8, 10 have a common factor of 2. And if we divide 6, 8, 10 by 2, we get 3, 4, 5. So these two triples are basically counted as the same. So the question for this video is, how do we find all primitive Pythagorean triples? For that, we need to take a closer look at the Pythagoras theorem itself. First, let's try reforming this equation by dividing both sides by c squared. Now let's set a divided by c equal to x and b divided by c equal to y. And after replacing these terms with x and y, we get this. X squared plus y squared equals to 1. And this is an equation of a circle. More specifically, the unit circle. That means we can graph this in the coordinate system and we get a circle at the origin with a radius of 1. This is very important here. That means that there are points x, y that work in this equation. Or another way to think about it is that all these points with the values x and y that lie on the circle work in the equation x squared plus y squared equals to 1. And if we find a point where x and y are rational, that means x and y can be displayed as fractions, we can replace x and y in our equation with these rational numbers. This whole equation can then be converted back to the Pythagorean theorem, and we've gotten another Pythagorean triple. So by finding all rational points on this unit circle, we find all Pythagorean triples. So good, now we've got a game plan. So, how should we approach this? Now the solution I'm about to tell you is not something you'll get very quickly by yourself, but I still want you to try and think about how to solve such a problem. Where would you start with such a question? We are using a method in which we first find one rational point on the circle, and from there we continue building more rational points. So go ahead, try finding one rational point on the circle. There are 4 obvious rational points, them being the points on the x and y axis in which the circle intersects. But for now, let's just look at the point 0, 1. Now let's say that there is a line going through the circle like this at this point. This line cuts through the circle at another point. Let's call that point P. And it also intersects the x-axis at a point which we are calling R. Now what we are going to do is prove that P is always a rational point. It doesn't matter how the line is constructed, it could even be on the negative side of the x-axis, it won't make any difference. But for now, let's keep it on the positive side. Let's say that the coordinates of the point R is R and 0. 0 because it's on the x-axis, so its y value is 0, and R because this point is not fixed, it could be anywhere on the x-axis. Now with this information, let's calculate the linear function for this line. For that, we're going to need its slope. The distance between capital R and the origin is r. The distance between the red point and the origin is 1. And this is the general form of a linear equation. And to calculate the slope, it's the y value divided by the x value. That means the slope here is minus 1 divided by r. And the n is the point where the line cuts the y-axis. That is 1. If you're wondering why it's minus, it's because this line is going downwards. To find the coordinates of the point P in terms of r, we substitute this whole equation into the equation of a circle. Then we get the coordinates of every point where this line intersects the circle, which is point P. Coming back to the function of the circle, x squared plus y squared equals to 1, let's replace the y with that linear equation that we've gotten earlier. And from here, it's a lot of boring plain calculations. I will put them on the screen. You can pause if you want a longer look at them. And I will highlight the most important part of this yellow. As you can see, in the end, we've gotten the x value of the coordinate point P in terms of r. And now, we can replace this x value back into the linear equation of the line to get the y value in terms of r. So let's go ahead and do that. Let's replace the x in the linear equation with its value in terms of r. If you do the calculations right, this will be your outcome. Now we're almost finished here. That means that this here is the x and y coordinates of the point P in terms of r. There's just one last thing to clarify. It's that r can only be rational. We can see that by reforming the linear function of the line. Now for our last step, let's replace r with p divided by q. That makes the points x, y turn into this. And now, let's just put x, y into the equation of the circle. And after some simplification, we get our answer. Now this looks very messy, but all that's important to understand is that we replaced r with p divided by q and put the values of x and y into the equation of the circle. And we're done. And that's it. We've reached the end. Thanks for joining me on this journey. We've gone from multiplying triples to graphing lines on circles to finding a formula for every Pythagorean triple. You've done a great job today. I would really appreciate it if you would like and subscribe if you've learned something. See you on the next one.